Most of the control circuits you find in industry must add a way of remembering the state of a device or in other ways to add memory to a circuit so that proper operation occurs. To understand it in a simple manner, let's take this example. If we want to have this magnetic motor starter turn on when the push button is pushed, we can simply have it connected like this, where the push button is driving the logic of the starter. Every time the push button is pressed, the motor will run. However, if the push button is released, the motor will be dropped and stop running. So, if we wanted to keep the motor running when we push the start push button, we would have to add memory, so to speak, to the circuit, so that it remembers that the start push button was pressed once. In order to add memory to the push button circuit, we must add a set of contacts in parallel to PB1. To accomplish this, we use the auxiliary set of normally open contacts available from the starter at terminals 2 and 3. This set of contacts close once the starter coil is energized and remains closed as long as the starter coil is on, thus providing memory that the starter coil is on. If the push button is released, there's still power continuity from L1 to the starter because the contacts M1 will seal around PB1. This circuit, however, has to be modified so that the motor can be stopped because, as it is right now, there is no way to stop the motor except by turning some main circuit breaker off. To be able to stop, we simply add in series a normally closed push button PB2, which we will call stop. There may be, depending on your application, more than one stop push buttons in the circuit. Some may be normally closed rope switches or other emergency stop push buttons which can stop the motor also. This is very common in industry and is a very good practice on the part of electricians and technicians working at the plant. Let's take this simple start-stop motor circuit from the beginning when everything is off. If we push the start push button, there is power from L1 to the starter, thus turning the starter on, in which case its contacts M1 will close, sealing PB1. If the start push button is released, the M1 contacts will continue to provide power to the starter. This circuit remembers that PB1 was pressed once. To stop the motor, we simply have to push the PB2 push button momentarily to break the power continuity to the circuit and therefore turn the starter off. Once the starter is off, its M1 contacts will go to their normal state, the normally open, thus not providing memory or a seal around PB1. The motor will not turn on until the start push button is pressed once again. In this motor control circuit, you could easily add an indicator light which will be on whenever the motor is turned on. If the motor is off, then the light will also be off. You may encounter or have to modify many motor control circuits in the plant to include several start or stop circuits, the so-called multiple start-stop. This simply means that you can start or stop a particular motor from different locations. When any start push button is pressed, the starter will be energized, seal the circuit, and turn the motor on. If you want, you may have motor indicator lights routed to where each start-stop circuit is physically located so that the operator may know if the motor is on. To review some of these circuits, let's take an example of a motor control circuit which our boss tells us needs to be modified. In this circuit, we have two independent motor starters being controlled by two separate start-stop circuits. We are told that we need to modify the circuit so that the second motor starter, M2, does not start unless M1 is already on, and that the start-stop circuits for M2 should stay the same, so that we could stop M2 without stopping M1. However, if we stop M1, both motors should stop. We can easily accomplish this by knowing that at this point, the circuit provides information with memory that M1 is running. So, if we connect our first line of our M2 starter circuit line 3 to this point, we would get available power for M2 only if M1 is on. Remember, because the sealed contacts M1 are providing power. So in this diagram, we could start M2 by pressing its start push button at any time after M1 is on. If the stop push button corresponding to M1 is pushed, then both circuits will drop. If M1 is not on, pushing the start button of M2 will not do anything. This type of circuit can be called a sequential motor because it will start M2 in a sequence after M1. As we have seen, the logic in a control circuit determines or defines how an output or load is going to be turned on or off, according to a need. When you are working on an electrical control circuit, you must understand the operation of the machine or be able to read the control diagram and find out about the machine operation and how to fix a problem if necessary. In dealing with all this, you will find certain circuits, especially in the control of motors, known as interlocking circuits. Interlocking can be defined as the means by which a device is actuated by the operation of some other device to which it is associated. Interlocking is used in a variety of circuits, but it is very frequently used in motor control circuits to prevent, for instance, a command for a motor to go forward and reverse at the same time. You'll find three types of commonly used interlocking techniques. These are the mechanical type interlock, the push-button interlock, and the auxiliary or control relay contact interlock. Mechanical interlocks are generally found in magnetic reversing starters, which allow the control circuit to direct the motor in a forward or reverse direction. This mechanical interlock is usually factory installed by the starter manufacturer. The interlock is made up of a mechanical linkage placed in such manner and position that makes it impossible to close both starter controls in the forward and reverse state at the same time. This type of interlocking is represented like this in a ladder diagram, where the dotted lines represent the mechanical interlock. The push-button interlock is another common technique of protecting two circuits from being on at the same time. This interlock is provided by a double circuit push button, having one set of contacts normally open and another one normally closed. In a forward-reverse motor control circuit, these push buttons are connected as shown. In line 1, the normally closed reverse, in series with the normally open forward, allows the forward starter to turn on when the forward push button is pressed. If the reverse push button is pushed, then the forward circuit will break and the reverse starter will be turned on. Note that this push-button interlocked motor control circuit provides instantaneous change from forward to reverse and vice versa without stopping the motor, whereas this mechanical interlock circuit would require the operator to first stop the ongoing direction of the motor before reversing the motor. A word of caution should be mentioned here dealing with the rapid reversal of a motor under full load. In many instances, motors and the equipment that provide power cannot withstand a rapid or sudden reversal of direction. Therefore, you must exercise care to determine under what load conditions you may execute a rapid motor reversal. You must also consider types of braking methods that may or must be provided to slow the machine to a safe speed before reversal. Another method of interlocking is provided by auxiliary contacts in control relays. This interlocking method is also referred to as electrical interlocking. These auxiliary contacts are also available in most motor starters to provide secondary interlock backup, even if mechanical interlock is already provided. In a motor control circuit like this, without mechanical interlock, we would add in series the auxiliary relay contacts R2 of the reverse starter in line 1 and the auxiliary relay contacts F2 of the forward starter in line 3. These contacts will prevent the forward and reverse starters from being on at the same time. Let's see it from the top. When no push button has been pressed, both of the auxiliary contacts, R2 and F2, will remain in its normal state, which is normally closed. If the operator pushes the forward push button, there will be power continuity from L1 to the forward starter. Its sealing contacts F1 will seal around the forward push button, and the auxiliary normally closed F2 contacts in line 3 will open because the starter coil is energized. These F2 contacts, now opened, will block any reverse push button activation of the reverse starter. If we wanted to reverse the motor, the operator would have to stop the motor so that the F1 seal is broken and the normally closed F2 auxiliary contact is back to its closed state. Now, the operator can press the reverse push button to reverse the motor direction. As you can see, interlocking forms an important part of control circuit design and troubleshooting. These interlocking circuits are used extensively not only in motor control circuits, but in many other machine control circuits where one event must prevent another one from happening, or if you want a condition to happen only when another one occurs. Let's take a quick look at a previous example. In Part 1, we had this control circuit where the light inside a panel would turn on and the power to the rest of the circuit would be removed if the door was open, releasing the door holding switch. An additional selector switch was added, which would allow an electrician to troubleshoot the circuit while the door was open, because power could be bypassed to the rest of the control circuit. In this circuit, however, if we close the panel door and forget to turn off the bypass power, the next time we open the door, the power will still be on because CR2 is energized. We can solve this problem by adding some interlocking and using a two-position selector switch with a spring return so that it acts as a momentary switch which goes back to off after being turned to troubleshoot. This modified circuit will prevent the bypass power from remaining on once the door has been closed. When the door opens, the contacts CR1-2 close to allow for bypass power to occur. Once the selector switch is momentarily put in troubleshoot, CR2 will turn on and seal the selector switch with contacts CR2-2 and provide bypass power. If the door is closed, the contacts CR1-2 reset the bypass coil and the bypass power. As you can see, a simple interlocking and memory addition can make a big difference to the desired action and improvement of a control circuit. Additionally, the components or control devices that you use during the design or modification of a control circuit are also important because, like in the case of the spring return switch, they will allow the circuit to be implemented. Let's now turn our attention to the interpretation of more complex ladder diagrams. We have previously covered some simple control circuits and the rules that we must follow to properly keep a ladder diagram in order so that other technicians and electricians can read it and troubleshoot it without getting a headache and then blame you for it. Control circuits tend to be larger and more involved than a simple 3 or 4 line diagram. But bear in mind, if you keep all information in proper order, troubleshooting and understanding a ladder diagram is done one line at a time and will not be cumbersome. But before getting to analyze a larger control circuit, let's review another rule that applies to ladder diagrams, which is the numerical cross-referencing of devices. The numerical cross-reference of devices is of extreme importance because it allows you to quickly locate a device connection. There are basically 3 devices or elements that are cross-referenced in a circuit. These are the normally open contacts and normally closed contacts of coils and the referencing of mechanically linked control devices, such as limit switches and others. As we know, relays, contactors, and motor starters usually have more than just one set of auxiliary contacts which are used for memory and interlocking purposes in the control circuit. These contacts may not, however, appear to be shown in a close location or proximity to its reference coil, but rather these contacts may appear at different and far-away locations in the ladder diagram, thus making it difficult for the electrician or technician to follow the effect of a control relay being energized and its reference contacts opening and closing and interlocking other circuits in the diagram. To reference contacts from coils, timers, and so forth, we place the line location number on the right-hand side, next to the element being referenced, where the element's contact is being used. If the contact element being used was a normally closed one, we would indicate it by placing an underline to the reference line number. For example, in this diagram, the timer TMR1 contacts are used in lines 2 and 5. Note that in line 2, the contacts are instantaneous contacts used to seal PB1, while the contacts in line 5 are normally open on-delay timer contacts. The same applies to all control relays in the diagram. In the case of mechanically linked contact elements, the representation generally used involves the use of dotted lines. Here, we would know that the limit switch LS1 has two sets of contacts, one normally open in line 5 and one normally closed in line 7. This representation shows the electrician or technician that this limit switch has an action on two ladder diagram circuits. If LS1 in line 5 closes, then the contacts in line 7 will open. Conversely, if the contacts in line 5 open, then its mechanically linked contacts in line 7 will remain closed. However, this type of mechanical representation using the dotted lines is useful as long as the two or more contact elements are not separated by an enormous number of lines. It would not be logical to have one set of contacts in line, say 3, in this case the temperature switch TS3, and the other one in line 10, shown with a dotted line linkage. Instead, you may find and use this type of nomenclature where it indicates the location of its mechanically linked contacts. In line 3, we can see that the temperature switch TS3 has another set of contacts normally closed in line 10. Note that we also include the underlined bar if the elements being referenced are normally closed. Conversely, in line 10, the temperature switch shows that there is another set of normally open set of contacts in line 3. So far, we have discussed the electrical symbols and connectivity of control devices and put them to work in ladder diagrams. Those diagrams showed us a way of determining and referencing very quickly how a particular control circuit will operate. We mentioned also that another way to represent parts of the operation was using wiring diagrams. Wiring diagrams, unlike ladder diagrams, are intended to show the actual connection and placement or location of components as close as possible, including the power circuits. Wiring diagrams are extremely useful to electricians and technicians while troubleshooting or designing a control system, since they provide you with a roadmap of the actual wiring. This is not more true than in motor control circuits, which, of course, use magnetic starters and other control devices. As we mentioned, the wiring diagram illustrates as close as possible the location of the wiring connections. In this starter, for example, you will find a wiring diagram like this, which shows all the connections to the starter, in addition to the location of the components within the starter. The symbols in the wiring diagram show the location of these components in the same manner where you would find them if you were looking at the starter from top to bottom. From the top, you have the three terminals that connect to L1, L2, and L3. Immediately below the power terminals, you will find another three terminals shown in smaller circles. These terminals represent and are used for the wiring connections of control circuits, which will be represented in thinner lines as opposed to heavy lines for the power circuits. We'll see these connections in a second. Right below, we find the actual contacts that will turn the motor load on, and below we have another set of terminals which are normally used when we have reversing circuit connections. These can be considered power connecting terminals as opposed to control circuit terminals. Under this second set of power terminals, we find the starter coil represented in the diagram in the middle cross-section, which is the location where you will find it in the starter. Also shown are the two terminal connections that are used in the wiring of the control circuit. Note the smaller, thinner-lined circles which symbolize the terminal connections for the control circuit. When the coil is energized, the motor load contacts close, which in turn start the motor. On the left of the coil are located the auxiliary contacts, commonly used as interlocking or sealing contacts. The terminals are labeled 2 and 3. Depending on the starter, you may also have another set of auxiliary contacts normally open or normally closed. On the lower left, you'll also find the normally closed overload contacts. Depending on the starter, you may find three sets of overload contacts, one for each heater coil. If this is the case, you would connect or wire them in series if they do not come internally connected. Although most overload assemblies provide one set of normally closed contacts for all three power line circuits, if there is an overload in any of the three lines, the overload contacts will be tripped. At the right of the overload contacts in the diagram are represented the overload heaters, which control the overload contacts. Note that the terminal connectors for the heaters are in bold lines to signify the presence of a power circuit. Finally, below the heaters, you'll find the terminal connections T1, T2, and T3 that would be connected to the motor load. In this case, of course, the connections will be for a three-phase motor. Most of the time, you will find starters that come with some pre-wired control circuit connections, which are done at the time of manufacturing. These include one side of the starter coil to terminal 3 of the auxiliary contact. This connection will be represented in the wiring diagram like this. Another connection might be from the back side of the coil, so to speak, to the one side of the overloads. This connection will look like this in the wiring diagram. The other side of the overload will be connected to the L2 line in the control circuit, just as it is represented in the ladder diagram. The layout and connection diagram provides electricians and technicians with the physical control panel location of the components used in the ladder diagram. Therefore, before we can start selecting an appropriate panel or enclosure for the control circuit components, we must know the number and size of the components we're using. Thus, we can begin a preliminary panel layout. Let's go over a simple example, since it is better to explain it as we go along. Let's assume that we have this ladder control circuit, and now we need to put it physically together. Here we are going to use a control transformer for the 120 volts power between L1 and L2. We can start the layout by assigning areas that will be used by the components we have in the circuit. That is, the control relays, the transformer, the fuse block, and the disconnect means. We can create a layout skeleton by positioning the components like this and leaving spaces for future expansions if necessary. We are going to use control relays with two normally open set of contacts for this particular application. As you can see, the inside panel conduits will be used to route each of the connections to the terminal block on the left. The control sensing devices, such as the limit switches, that are mounted on the machine will also have their wires brought into the panel's terminal block. We'll label the connection later. In the panel layout, we would place the components like this, so that we could route the wiring according to the terminal blocks. The terminal block labels where each component to be wired will be determined from the assignment of connections in the ladder diagram. From this ladder, we can say that for the L1 power, we'll be using terminal block label number 1, and for the return L2, we will use terminal block number 2. Because there will be many wire connections going to L1 and L2, we'll assign a block to each with several terminals with label 1 and label 2. The rest of the wiring connections will be assigned as we go through each circuit. That is, this side of PB1 will be wired to terminal 3, which also connects the ceiling contacts CR1-1 and PB2. The other side of PB2 will go to terminal 4, which connects to the other side of CR1-1 and to one side of CR1 and to one side of PL1. The other sides of the coil CR1 and the light PL1 are connected to terminal 2. The rest of the control circuits would follow in the same manner. In the panel, the wire connections will be represented like this, where each wire will be sent to the terminal blocks via the conduits. In the machine diagram, we would also signify the terminal destination to each of the control devices being used in the circuit, these being the limit switches and the solenoid. As can be seen, the routings go to the terminal numbers assigned in the ladder diagram. As you can see, a properly documented layout diagram can be of tremendous help during the installation and troubleshooting of a control circuit. You would immediately know where each device is connected or terminated. In this training module, we have covered some important control circuit topics that will certainly help you not only understand control circuit ladder diagrams, but also help you considerably during troubleshooting of a system or making circuit changes to an existing machine.